Kia ora and welcome to question 2 of the 2010 Skull Calc exam. In this question we've got quite a neat region that involves hyperbola and lots of symmetry. We've got to find some areas of the circles in those diagrams. We need to find the area of the regions that are shaded, so that uses integration. And the second part, part B there, is a curve where we need to find its second derivative and then find points of inflection. Okay, so this first one here starts off with some hyperbola. It'd be useful first up to work out which hyperbola was which. So a is a positive number, 1 plus root 2 is positive, so x squared minus y squared equals a positive number. It gives us, what am I going to do, highlight this in green, it gives us this one and this one. Okay, and it's a real easy check there. If you make y equal to 0 to find the x-intercepts there, you're going to be solving x squared equals 2 times 1 plus root 2. You square root that and you get a positive number and a negative number. You get two solutions. And that corresponds to the fact that hyperbola there's got two x-intercepts. And it's the only hyperbola that's got x-intercepts. So you didn't need to know anything about conics to work out that. Just plot some points like you probably did in junior maths. This one here, y squared minus x squared equals 2a. It's just the other way around as you would expect, because you just change your x and your y around. It's like turning the page 90 degrees. Now xy equals a. X times y equals a positive number means that both of the numbers x and y must be positive, or both of them must be negative. So that one's going to be either in the first quadrant where both x and y are positive, or in the third quadrant where both are negative. And then lastly, just to complete, I better change the colour up again. We've got the last hyperbola, which comes in pairs there. xy equals negative a. The pink and the yellow ones there, they're level 2 mathematics in NCA level 2, because they can be rearranged as y equals alpha plus or minus, no, not plus or minus, my bad, just alpha over x. And the other one is negative alpha over x. Okay, how is that helpful? The first question tells us that we've got a circle inscribed in the central region and another circle circumscribed around it. Find the exact area of each circle. So the inner circle, it turns out we need those x-intercepts or the y-intercepts of the hyperbola that are opening outwards and opening up and down, because that will give us our radius. So take the hyperbola that's opening up left and right. I'm just going to leave this in terms of alpha, and we want to find the x-intercepts of this by making y is equal to 0, x squared is equal to 2 alpha, so x is plus or minus the square root of 2 alpha. Now we don't need those x-intercepts, right? We're wanting the area of the circle. The area of the circle, and we'll call this a small circle, is equal to pi times radius squared. The radius of that circle is the distance from the origin to the x-intercept. So we're going to be squaring that x again anyways. So it's going to be equal to pi times x squared, which is 2 alpha. And we could then put pi times 2 times 1 plus root 2 in. And if you really want to work it out as a decimal, then you can. But the question I did ask you for the exact form, I believe, so working out as a decimal is only helpful to know roughly whether you've got the right size there. So it comes out to be 15.17. Let's see what the question said. Find the exact area of each circle. So yeah, don't give the decimal as your answer, because then it shows that you don't understand what exact means. Okay, the second circle, to find that out, we're going to need to find the point of intersection of the hyperbolas. In this case, then maybe the yellow and the green one. So if we find the point of intersection, then we can use a distance from the origin out to the point of intersection as the radius, and that's going to be x squared plus y squared square rooted. But again, we just need the radius squared because pi r squared. Alright, so solving the yellow and the green together. Finding the points of intersection that are relevant. I'm going to solve the green one again, which is x squared minus y squared equals 2 alpha, along with the yellow one, xy equals alpha, or y is equal to x over alpha. No, alpha over x. Notice I'm leaving alpha in there as long as possible because I really don't want to have to work with 1 plus root 2 every single time, particularly if I'm going to find the exact answers to these problems. Okay, so doing that, substituting one equation into the other, we've got x squared minus alpha over x all squared equals 2 alpha. I could times the whole thing through by x squared. That's going to give me x to the 4 minus alpha squared equals 2 alpha times x squared. It's a polynomial now. It's a disguised quadratic. If I rearrange it, x to the 4 minus 2 alpha x squared minus alpha squared equals 0. I don't need to find x here. Finding x would give me the point of intersection, but I need x squared because I need to use Pythagoras to find the radius. So I just need to solve for x squared, meaning that I could complete the square on this rather than use the quadratic formula. I could write x squared minus alpha all squared. That's going to give me x to the 4 minus 2 alpha x squared plus an extra alpha squared that I don't want. So I take that away with the other alpha squared that I already had, and you can check by pausing that is the correct factorization. Then I rearrange it. Therefore x squared is equal to alpha plus or minus the square root of 2 alpha squared, or alpha plus or minus alpha times root 2, or alpha times 1 plus square root 2. Positive root only, because x squared needs to be a positive number, and 1 minus root 2 would make it negative. And the equation that we were solving, there was a power of 4 equation. It's going to have two real solutions. It would have two that are complex. We don't want the complex ones, or the ones with imaginary bits. We don't want those. Okay, so that's x squared. And remember that y was equal to alpha over x for this particular one. So y squared is equal to alpha squared over x squared, which when we substitute the x squared bit in here, we've got alpha squared over alpha squared times 1 plus root 2 all squared. The alpha squareds cancel. Was I expecting that to happen? It's kind of interesting that it didn't square when I had the x squared, but then when I chucked it into the y squared, it did. That's because I've squared it. I've squared it when I shouldn't have squared it. Alright, because I have x squared here, and I'm subbing in x squared, not subbing in, I don't need to square it. So I'm subbing in alpha, 1 plus root 2. So only one of the alphas on the top will cancel with the alpha on the bottom. So it's alpha over 1 plus root 2. And I could times by the conjugate here, times it by 1 minus root 2 over 1 minus root 2. By doing that, the denominator goes to negative 1. The numerator is alpha times 1 minus root 2. Because the denominator is negative 1, it's going to switch around and be root 2 minus 1. Okay, so that's y squared. How's that helped? The area of the large circle is pi r squared, which, as I said earlier, is Pythagoras, is going to be x squared plus y squared. In there, pi x squared was alpha times 1 plus root 2, and we're adding on alpha times root 2 minus 1. The 1's cancel there. The 1 cancels over the minus 1, and we've got 2 root 2 alpha in there. So 2 pi root 2 alpha. Now what was alpha? Alpha was equal to 1 plus root 2. So if we expand that out, we've got 2 root 2 pi, 2 root 2 plus 4 all times pi. Alrighty. Okay, now they give us this kind of neat figure 3, which you'd probably never have picked up, at least I told you. The areas of the two shaded regions in the figure 3 are the same. Figure 1 is 8 times the area of a shaded region in figure 3. Yeah, well, I mean that's obvious, because if we take this region here and then we just copy it because of the symmetry, right? It's 1/8 of the total region. We're trying to find the exact area of the entire inner region of figure 1, which is the same as figure 3, right? We're trying to find this region here. Ignore the circles is basically what they're saying. So to do that, we could use polar integration, if you've heard of it, because polar integration is all about integrating around the origin. But the reason why they've shown us that this region, well, these two regions have the same area, is because we can use integration, like normal integration here. Normal integration, what is that? From left to right. So that's what we'll do. So, okay, to find this region in here, we just need to find the intersection points. So we've already actually found one of them, because when we solved the green equals to the yellow, when did I do that? I came out with x squared equals alpha times 1 plus root 2. I came out with it down here, right? So the square root of that would give me the x value that I need. That's my limit there. This alpha times 1 plus root 2. Drawing too small. Alpha 1 plus root 2 square rooted. Okay, that there is that right limit, and it would be the same on the other side, just negative. And then what I need to do is also solve the blue equals to the pink. Okay, so solving the blue equal to the pink, what do we get when we do that? I'm sure we could probably use symmetry to do that as well. How are we going to do that? Yeah, definitely we can. Because if we look at the y value we found earlier, the y value is going to be the x value, again negative, on the left hand side there. So why am I keeping on working on the left hand side? I don't need to do that. Let's work on the right hand side. I think they just did it for the diagram for simplicity, but let's just work with the area here. Then we don't have to do negatives with our limits. Okay, now if I solve the yellow equals to the blue, that's going to give me the other x value, which, as I was saying, is just the y value of the other point. Okay, so I don't need to do any more solving. I just used the y value, which was down here. Well, that was y squared, so square root that. That's my other limit. Square root of alpha times root 2 minus 1. Okay, and I'm integrating the yellow curve, which is alpha over x between there. It's y equals alpha over x. Okay, that will find my blue area, then I times it by 8. Wowee. Okay. Area equals 8 times the integral of alpha over x dx between the square root of alpha times root 2 minus 1 and the square root of alpha root 2 plus 1. Root 2 plus 1, I can't believe I didn't notice that earlier, but root 2 plus 1 was alpha. So actually that yellow limit there, root alpha times 1 plus root 2, is actually just equal to alpha. Oh my goodness. I definitely should have spotted that earlier. Okay. So let's just make, oh no, it wasn't that one. It's that one. Let's just make that one alpha. Alrighty. Well, what's the other one going to be if I make alpha root 2 plus 1? Now, I said keep in alpha as long as possible. I should have eventually got rid of it, right? So if I put alpha into the bottom limit, it's 1 plus root 2 times root 2 minus 1. That comes out to be, well, the root 2's cancel, that's a good thing, and we get 2, oh wow, we get 1. So the bottom limit's 1. Oh my goodness. Okay, so that there blue limit equals 1. Alrighty, so we're integrating a very simple expression now after all of that. Alpha times log of x, because it's 1 over x there, in between alpha and 1, which equals 8 alpha times log of alpha, where alpha's positive, so I don't need the absolute value symbols anymore. And then if I put in the lower limit of 1, log of 1 is 0. So that's my answer there. And again, if you want to sort of get an understanding of how big that is, the region we've just found is slightly bigger than the smaller circle that we had earlier, the circle that was inscribed in there. Our region's got to be slightly bigger because it's going to include these little extra starry bits that we didn't include. And it's also got to be smaller than the region of the bigger circle. So if we go back to the 15.17, which I said, hey, let's ignore this because it's not exact, our answer to this question should be a bit bigger than 15.17. And if I evaluate this 2 root 2 plus 4 times pi thing, that's going to give me a sort of an upper bound that my answer should be less than. So if I do that, that comes out to be 21.45, but I believe. But again, that's not the answer for that one. So our answer should be somewhere between 15 and 21. Okay, let's evaluate this now. 8 times 1 plus root 2 ln of 1 plus root 2. And that comes out to be 17.02, which is exactly in between those numbers that I wanted it to be. Brilliant. Okay, part B in this question was a curve, the cube root of x times e to the minus x squared. It might pay just with curves just to make a graph of them on your graphics calculator and have a look, because often that can be a giveaway as to what we're actually dealing with here. So rather than do that, I'll do that on Desmos. Okay, so y equals the cube root of x. The cube root of x is an interesting function in itself because it has a point where the gradient is undefined. That vertical part at the origin. I think that's what the crux of this question is asking us about. And then we've got e to the minus x squared in as well. So e to the power of minus x squared. Alrighty, so we can see that there are 2 points of inflection. One's at about -1, one's at about +1, and then the origin is where it goes from concave up to concave down. So it is a point of inflection, but it's vertical, so its gradient's not defined there. Okay, let's go back to the question. So let's differentiate this thing twice. Okay, so to diff this curve here, we need the product rule. We diff the first term, third x to the minus 2/3, multiply by the second term. Then we diff the second term, e to the minus x squared diffs to itself, times minus 2x, that's the chain rule, times by x to the 1/3. And normally I would factor at this point, but I need to diff it again. So I've got an option. I can either use the product rule on both of the terms individually or do a little bit of factoring. E to the minus x squared feels right to pull that out, but then I leave the other bracket as just everything else. If I factored this, then I'd end up with the product of 3 terms, and whilst I can actually differentiate a product of 3 terms, f, g, h dash actually just equals f dash g dash g h, g dash fh h dash fg. You can verify that yourself. To do that, you just treat f and g as one single term and use the product rule once and then repeat it. But yeah, I don't bother factoring out any more terms because I don't want to differentiate a triple product. Okay, so second derivative, diff the first term times the second bracket, diff the bracket, times the first term. Okay, and now we're going to factor because we want to solve it equal to 0. The question said that the points of inflection aren't necessarily where the second derivative equals 0, so where it changes sign. And if you think about the graph y equals x to the 4, when we diff that, 4x cubed, and diff again, 12x squared, that equals 0 at x equals 0, but x equals 0 is actually a minimum because the second derivative there is always positive except for 0, so it never changes sign, and therefore it's not a point of inflection. It's in this case a minimum. If you graph y equals x to the 4, it looks like a really flat parabola. So that's kind of what we're doing here. We're going to look for that vertical point of inflection, which won't be where the derivative equals 0 because I explained earlier it's where it's undefined. So pulling out the e to the minus x squared term, we also pull out the most negative power. So the most negative power turns out to be x to the minus 5/3. And that comes from this term in here. What do all the other terms give? The first bracket, we've got an x outside and an x to the minus 2/3. And that's going to give x to the power of 1/3. We've already pulled out minus 5/3 in our factorization, so we need 6/3 as the power inside, 6/3 is 2, and the coefficient we want is minus 2/3. Then we've got a plus 4 multiplied by x to the power of 7/3. Pulling out minus 5/3 means we need 12/3. 12/3 is 4. Then we've got the minus 2/9. And the last power is 1/3. We've already pulled out a minus 5/3. So again, we need a 6/3, which is a 2. So it's minus 8/3 x squared. Now I don't like the fractions here, so I'm going to pull out a factor of minus 1/9 by timesing everything in the brackets by -9. When I do that, the first thing becomes 6, and then negative 36x to the 4, then plus 2, and then times in the last thing by -9 gives me plus 24. And I've got some like terms there. And I think this is the format that the question asks for it to be factored in. It doesn't tell us that A, B, and C in that quartic needs to be a whole number or anything, but it turns out it does if I factor out that minus 1/9. Okay, so we've got negative 36x to the 4 plus 30x squared plus 2. Okay, solving equal to 0 is we've got a disguised quartic there. Sorry, disguised quadratic out of the quartic. So x squared equals minus b, negative 30, plus or minus the square root of b squared, 30 squared, minus 4 times negative 36 times 2, all over 2 times negative 36. So I've treated, this is the a, this is the b, and this is the c, used a quadratic formula, but I'm solving for x squared and not x. If I do that, they're not actually nice numbers or anything. And remember, I was expecting them to be about plus or minus 1, because that's what the graph showed me. The points of inflection look like they're about plus or minus 1. So if I just evaluate these as decimals, minus 30 plus It needs to be the plus root, otherwise the x squared thing will be, or not. No, because the denominator there's negative, which means that the numerator needs to be negative as well. Otherwise we're getting x squared equals a negative, and we don't want that. So minus 30, and then if we subtract the square root of 900 minus 4 times negative 72, and then divide it by minus 72, that comes out to be, my calculator's still got thirds, but decimals at this stage is fine because they ain't nice numbers. Oh, not plus or minus at this point because we've just taken the minus root. 0.8954 to 4dp. The square root of that is plus or minus the square root of the decimal, 0.9462. Okay, so those are points of inflection, because if we look at the other parts of the expression, this is always negative. It's an exponential with a minus negative coefficient. And the x to the minus 5/3 term, what does that equal? Well, that alternates sign. So if we're slightly to the left of the x value we've just found, or slightly to the right of the other one, it pays to maybe use the second derivative test here. Because we've got the second derivative already, we might as well use it. So subbing in these values, well, sorry, if I sub them in, it's going to get 0. I need to sub in values either side of it so that I can test whether the concavity changes. So if I sub in minus 1 into the second derivative, the first term, like I said, was negative. The minus 1 to the power of minus 5/3, well, what does that equal? That's a complex number. Interesting. Have I got my calculator on complex mode? Yep, I do. Changing my calculator to real mode and taking the real one, I get -1. Oh, crisis averted. Okay, so the second derivative, the substitution is really tedious. That second term is -1, but the first term in it is negative, and I've also got to test the quadratic. I'll leave you to do all the substitution, but it turns out that if I sub in -1, I get a negative into the second derivative there, and if I sub in negative 0.9462, I get 0, and 0.9462, I get 0, and subbing in 1, I get a positive number. And then why did I leave a gap there? Because 0 is a special case. 0 is where it's undefined. So I actually need to test a value in between minus 0.9 and 0, and between 0 and 0.9, to see that there is a change in sign there. And you get 3 points of inflection. There are 3 points of inflection. The 2 that we found, the plus or minus 0.9462, and x equals 0 is as well, because there is a change in sign in the second derivative.